Welcome back. So far, we've looked at the constant rule. Derivative of a constant function is zero. We've looked at the sum and difference rules. So derivatives of things being added or subtracted, we can go term by term, finding our derivative. We've also got a constant multiple rule, which is if we have a function where it's differentiable and we've got some constant multiple of that function, some real number. So here I've got f is some differentiable function. In other words, that's telling me that f prime exists, and I know what f prime would be. F prime is the limit of our difference quotient. So provided that I know that f prime exists, and provided that k is some real number, and if I'm looking at a function k times f, then that's also should be differentiable. And to find the derivative, it's just k times the derivative of f. So not a very surprising sort of a thing. We had a similar kind of an idea for limits. If it was limit of k times something, it was k times the limit. Derivative of k times something is k times the derivative. Same sort of an idea. Of course, the proof, not too terrible for us. If we're looking for the derivative of k times f of x with respect to x, well then all we need to do is get out our difference quotient and get to work. So limit delta x approaches 0, k times f of x plus delta x minus k times f of x all over delta x. And then we're almost finished. And the reason we're almost finished is I notice that I have two terms in the numerator that both have a k. So in other words, k could be factored out of the top. And in fact, if I wanted to, I could rewrite it instead of k times the numerator. I could write it as k times the fraction f of x plus delta x minus f of x over delta x. So I've taken that k that I originally had in the numerator and I have completely factored it out. And again, a limit rule that we had, which was if you have two things that are being multiplied and if the limit exists for each of those factors, then the limit should be just limit for the first thing times limit for the second thing. K is a constant, so as delta x goes to 0, it'll just stay as k. F of x plus delta x minus f of x over delta x, all that business. As delta x goes to 0, that's my derivative of f prime. So both limits exist, so the limit of k times that difference quotient should be k times the derivative. A new rule to look at, and this is a very useful rule, the power rule. So you'll notice here we're putting some limits on things, not just any old x to any power, but specifically x to a power of n that's a rational number. We're doing this on purpose because later on we're going to prove the power rule in general for any real number n, not just the rational ones. There is a proof of the rational number power rule. It's not an easy proof. The one for the positive integer powers of n power rule, so even more restricted. That's a relatively straightforward proof. But we're going to see that to prove the power rule in general, we're going to need some heavier machinery, in particular logarithms and exponential functions, which we're going to get to towards the end of the course. So know in your heart that the power rule will work for any n, but at least for now, for our theorem, n will have to be a rational number. We're also not going to be proving the power rule just yet. So the power rule is something we'll need to know how to use, but we won't need to know how to prove it. Power rule is easy to use. For x to any power, the derivative is found just by bringing the power down and reducing the power by 1. A couple of little side notes for us, of course, to remember here. Number one is that if we're thinking about this, if n can be any rational number, there may be some limits on where the derivative exists. So for example, if you're thinking about the square rooting function, square root of x, which is the same thing as x to the power of a half, you can find the derivative, but the derivative will not exist when x is 0, because remember, derivatives exist at points where there's an open interval with that point inside of it. Since 0 is an endpoint, there's not going to be a derivative at 0. We're also going to see for other powers of n that the derivative may or may not exist at all the values. So we'll talk a little bit about that later on. So the big thing here is, as I said before, for f to be differentiable, then when we reduce our power by 1, whatever that function is needs to still be defined on an open interval containing that point that we're interested in. So if we're looking for a derivative to be existing at 0, then whatever the function is has to be defined when x is 0, and it has to be defined around when x is 0. So for this, for f of x equals square root of x, is f differentiable at x is equal to 0? And the big answer for this one would be no. And the reason I know for that is if I were looking at the square root function, 0 does not exist inside of an open interval. There's no graph on both sides of 0. So unfortunately, there won't be a derivative at x equals 0. There's no tangent line there. And in fact, if you tried using the power rule here, that gives you another reason why the derivative wouldn't be 0, wouldn't exist at 0. If f of x was x to the 1/2, and you looked at finding the derivative, power rule would tell you you'd bring the power down, you'd reduce the power by 1, you'd have 1/2 x to the negative half, which is the same thing as 1 over 2 times square root of x. So again, pretty clear here that when x is 0, f prime is not defined. On the other hand, something like y equals x cubed, that's definitely going to be differentiable at x is equal to 0. I know that because if I looked at what my derivative is a nice function. It's 3x squared. That totally does have a value when x is equal to 0. And so yes, g is definitely differentiable when x is equal to 0. Okay, so let's find the derivatives of these functions. For this first one, I'm going to do probably way more work than I would expect you to do. I just want to sort of, for the very first time, show me using all of the derivative rules one by one. So if I'm looking at the very first problem, f of x is this function, x squared minus 3x plus 9. If I'm looking at finding my derivative, I can see that I've got 3 terms that are being added and subtracted from each other. So my sum and difference rules say that if you want the derivative of that function, I would need to take the derivative of the first term and then minus the derivative of the second term and then plus the derivative of the third term. The other thing that I might notice here, as far as the second term goes, that's actually a constant multiple. That second term, 3x, is 3 times x. So actually, when I'm looking at the derivative of 3 times x, I could use my constant multiple rule and say it's actually 3 times the derivative of x. And so now I can use power rule to help figure out the rest of this. I could say, well, for the first term, I've got the derivative of x squared, which is 2x to the 2 minus 1, which is 1. For the second term, I have the derivative of x, or x to the 1. That derivative would be 1 times x to the 1 minus 1, which is 0. And for the last term, which is 9, that's just a constant function. A derivative of a constant is just 0. So we wind up with our derivative being 2x minus 3. One thing to notice here is how much less effort this takes than using the limit definition. Once we get used to using power rule rather, and sum and difference rule and constant multiple rules, we won't have to do all the writing. And in fact, I'm going to do a lot less writing for the next few examples. Sometimes you may have to do a little bit of thinking, though, first before you find your derivative. I know for sure I'm going to go term by term because I've got 3 terms just like I did before. I also can see that I've got a constant multiple, 7 times this cube root of x. So I know when I do the derivative of that second term, it'll be 7 times the derivative of cube root of x. But it's probably a good idea first, before I do anything else, for me to think about rewriting these in ways where I could actually use my power rule. Instead of thinking about square root of x, I'll think about x to the half. And instead of cube root of x, I'll think about x to the power of 1/3. And so now if I'm thinking about doing my derivative, I can do that fairly easily, going term by term, taking out constants, and using power rule. The first term, x to the 1/2, the power comes down. I'll reduce the power by 1. 1/2 minus 1, that's negative 1/2. 7, my constant multiple, I'll leave that out front, and now I'll do my derivative of x to the 1/3. X to the 1/3, power rule says that the power would come down and that I would reduce the power by 1. 1/3 minus 1, that's negative 2/3. And then for the last term, minus 1, that derivative of a constant, that derivative is 0. And then the only thing left for me to do is maybe clean things up a little bit. Instead of having x to negative 1/2, I could put x in the denominator and make it x to the positive half, or square root of x. For the 7 times 1/3, I'll make that 7/3. And instead of x to the negative 2/3, I'll put x in the denominator as x to the positive 2/3. Nice. I'm not going to do anything further with this, and what you might do depends on what your goal is. So if I were looking to solve for x for some reason, then maybe it might make sense to combine the 2 terms, simplify things further. Maybe I'm just going to evaluate the derivative at a particular value of x, in which case, why bother simplifying at all? So what you'll need to do really will depend on your goal. Here, we're just finding the derivative, so I'm not going to do much further work as far as the simplification goes. Last one, h of x. Again, same thing as before. I'm going to rewrite these in a way where I can actually use my power rule. X in the square root in the denominator is x to the power of negative 1/2. And an x cubed in the denominator is really x to the negative 3. So now if I'm thinking about finding the derivative, I'll use my power rule. Power will come down. Reduce the power by 1. Negative 1/2 minus 1 is minus 3/2. And then for the second term, that 9 is a constant multiple. We'll leave it out front. Derivative of x to the negative 3 will bring the negative 3 in front, and we'll reduce the power by 1. So negative 3 minus 1 is negative 4. And then just a little bit of cleaning up again. For the x to the negative 3/2, I'll move that to the denominator and make it x to the positive 3/2. I'll multiply the 3 and the 9 together to get 27. And instead of x to the negative 4, I'll move it to the denominator and make it x to the positive 4. Okay, so a little bit of excitement. We've done a problem like this before where we found the tangent line to some curve at a point, and it was a lot more work in the past because we were using difference quotients and limits to do so. Now we want to find the equation of a tangent line at a point, and this is going to be much easier to do because I'm going to find my derivative using the differentiation rules we've done before. So first thing, if I'm looking for the equation of a tangent line, I know that I'm going to need to find, number one, my slope, and number two, I'll need to know what my point is. I have part of the work already done for me because I know where my point is. My point is when x is 3, and I know where the y value is. I find that by putting 3 into my original function. So we have y is 9 plus 3 minus 12, which is 0. So we've got the point 3, 0. So my tangent line is going to touch the curve at 3, 0. And for the slope of my tangent line, that's finding my derivative. So to find my derivative, I'll go term by term for my function using power rule as I go. For the derivative of x squared, that's 2x to the 2 minus 1, which is 1. For the derivative of x, or x to the 1 comes down and we reduce our power by 1 to get 0. For 12 is a constant. Its derivative is just 0. And so there we go. We've got our derivative happens to be 2x plus 1. And now I can use that to find what my slope is. I want to know my slope when x is 3. In other words, what is my derivative when x is 3? And to do that, I'm just going to put in 3 for x into my derivative, and I find that my slope is 7. So now I've got everything that I need. I have my slope of my tangent line should be 7, and the point that my tangent line crosses through should be 3, 0. And so I guess I'll finish it here. I didn't leave myself a blank page, so I guess I'll find my line, my tangent line, and that is y minus the y coordinate equals slope times x minus the x coordinate. And I have my y coordinate for the point is 0, my slope is 7, my x coordinate is 3, and so the equation of my tangent line is y equals 7x minus 21. So compare that to the very first problem that we did with finding the equation of a tangent line, and notice how much less work we've had to do. There's going to be several more differentiation rules that we'll cover as we go through this course, and as we add them on, it can make things a little bit more complicated as to the kinds of functions we can look at, but it also, in general, reduces our workload in the long run. If you're comparing it to doing things with limits and difference quotients, that's always going to be way more work than using our derivative rules.